Okay, so hi and good day again everybody. Welcome again to Principles of Reinforced Concrete. And in today's video, this is to be a continuation of, well, of course, the previous videos, and we would be discussing about the design of doubly reinforced concrete beams. So the design of doubly reinforced beams is kind of straightforward already if you are familiar with this diagram or this stress diagram. So in this stress diagram, we have here the compressive stress as brought about by the concrete. We also have the tensile force as brought about by the tensile reinforcement, and the difference between, of course, your doubly reinforced beams and that of your singly reinforced beams is that in your doubly reinforced beams, of course, you would now be having compression reinforcement. It is to be by these steel rebars. And well, in our stress diagram, it is already included here. So AS prime, FS prime. So once again, guys, the design is very straightforward if you already know this stress diagram. And if you have already watched the previous video lecture that I have posted, I have already included there this stress diagram into parts. So if we would be dividing this into parts, so let's say that this is to be the first part, and let's say that this is to be the second part. So what I did there was that I just separated ASFS prime by the requirement of this section in terms of singly reinforced beam. So in Tagalog or in Filipino, ang doubly reinforced beam natin is to be the addition or yung pinaghalo natin na singly reinforced beam plus of course the additional reinforcement. So if I am to draw its stress diagram, so from before, if this is to be your stress diagram for singly reinforced beams, so for a moment, so let's say that this is to be the diagram for your singly reinforced beam. So of course, you have here your 0.85 FC prime AB. So the resultant here, so let's, for example, that this is to be the resultant, that is to be 0.85 FC prime AB. And for its tensile force, as brought about by the tension reinforcement, it is to be your ASFS. So there. But here, guys, since this is to be a doubly reinforced beam, we are assuming that for the singly reinforced counterpart of it, it would now be maximized. So with that said, guys, no, so sagad siya. So for example, that you already have your Romax. So your Romax, and from your Romax, you already have your AS Max. So in your DRB, we are to assume that all of this is to be used here. So magagamit lahat ng AS Max. So with that, guys, instead of ASFS, this is now to be equal to AS Max FS. So once again, guys, reiteration that you will only be designing doubly reinforced concrete beams if let's say that your AS required is to be higher than that of your AS Max. Because if it is to be the other way around, if let's say that your AS required is to be less than your AS Max, you do not need to design doubly reinforced beams. Because in this case, you can just design it you can just design it in SRB. So SRB lang siya pag mas mababa yung AS required natin as compared with your AS Max. So once again, that is to be the main idea here. So that is to be the main appeal. Okay, and since our AS required is greater than your AS Max, using AS Max FS would rather be inadequate kasi nga kulang siya. That is why we would be introducing them here. So let's say that this is now to be your AS1. So AS1 FS. So take note that this FS here is also to be the FS here. Okay, and since we would be adding this AS1FS to maintain equilibrium, we would now be adding another AS here. So let's say that it is to be this one. So let's say that it is to be this. And this force right here is to be your is to be the compressive force as brought about by your compression reinforcement. And that is to be your AS prime, FS prime. So once again, that is the appeal. Okay, so when we are to design doubly reinforced beam, the first thing that we should take into consideration, or the first thing that we should check, is if we really need it. So instead of using AS Max, so we can actually break them into components, no? For your doubly reinforced beam, so of course you would be having here your AS prime. So let's say that this is to be your AS prime. So take note guys that in my example here, our beam is to be subjected with positive moment. So when we say positive moment, it means that the one on top, so this is now to be my compression area or compressive. Well, basically compressive area. So if this is BW, this is now to be A. So this is to be our compressive area. And with that guys, if this is to be your AS prime, this is now to be your AS. And this is to be the tension reinforcement. So this is now to be your AS. So if this is to be your doubly reinforced beam, so your doubly reinforced beam once again is to be equal to the SRB or yung kaya lang buhatin ng SRB. So this is to be the maximum SRB that it can carry, plus of course the additional steel rebars that it needs for it to be a doubly reinforced concrete beam. So once again, this is now to be your AS max. So with that, this is now to be your AS maximum. And well, in this case, guys, so by the way, this you still have your compressive area here. So this is now to be your compressive area. So if you can remember, which you should, so this is to be your 0.85 FC prime AB and etc. So it is to be this. And since we are lacking, let's say AS, so we need to have an additional AS. So assuming that your AS required here is to be higher than AS max, so we would be having another AS here. So AS1. And once again, to maintain equilibrium, we would now be adding steel reinforcement at the compression side. So this is to be AS prime. So guys, take note that your doubly reinforced beam is basically the addition of SRB plus the additional requirement. So I don't know what we would be calling this. So lagay na lang natin dito, I don't know. So I don't know what to call this section. So let's say that this is to be your 2 or yes, I don't know. Basta yun. Anyway, so moving forward guys, so when we are to to be designing doubly reinforced beam, so these are to be the typical steps. Of course, the first thing that you should do is for you to get the loads. And if you would be getting the loads, you would undergo, let's say, simplified method or other structural analysis subject matter. Basta kukunin nyo lang yung magnitude ng moment nyo. And after getting your moment, you would now undergo load factors. And by load factors, once you would be applying load factors, you would be you would now have your ultimate moments. So our goal is for us to get the ultimate moment MU. So that may be, let's say, your 1.2 dead load plus 1.6 live load, or let's say 1.4 dead load, and etc. So once again, the first thing that you should do is for you to get the ultimate moment. Then second is for you to get the nominal moment required. And if you can remember that your MU should be less than or equal to PMN. So your PMN here is basically the design strength. So design strength of your section. And from this equation, guys, we will now be getting the MN. So if we would be cross multiplying this, so from that, MN is now to be equal to MU divided by phi. So that, so there. And the value here, Mn, is to be the one carried by the whole doubly reinforced beam. So with that, guys, this is now to be your Mn, or the total nominal moment. Okay, so the next thing that you should be doing is that, so let's go to step number 3 already. So step number 3. So we will now check if we really need to design it as a doubly reinforced beam. So from that, guys, what you will be doing is that you will be drawing this setup. So I will just be copying this setup here. So you will now be solving for this setup, and now you will be solving for AS Max. But we have a catch here. So for your AS Max, we actually have two formulas. So if you would be considering NSCP provision, so in NSCP, it is indicated in NSCP that the maximum strain of the tensile rebars should be equal to 0.004. So this is to be one parameter, one, what do you call this, provision. And from our previous lessons, we have derived there the equation of, so for your rho maximum, that is to be equal to 0.85 times betas of 1 times fc prime divided by fy divided by 3 over 7. So if you can remember this equation. And this 3 over 7, of course, came from this equation. So that is to be strain u divided by strain u plus strain t. And once again, our strain u is equal to 0.003, as well as for the strain u, 0.003. And for your strain t, it is basically this. So that is to be 0.004. And simplifying that equation, you will now arrive at 3 over 7. Okay, so if you want to know more about that derivation, just rewatch our previous videos. Okay, so that is one rho max. So another rho max that we can use is the rho max by ACI. So American Concrete Institute, 318, and etc. So this other rho max, so the rho max, this is for us to ensure that it is to be a tension controlled. So rho max for tension controlled. And this is basically equal to, so 0.85 betas of 1 times f prime c divided by fy times 3 over 8. So in this, in this equation, the strain T here is to be equal to 0.005. Because if you can remember from before, once again, if this is to be your factors for phi, or the reduction factors for phi, so we have here 0.65, and we have here our transition zone, then we have here our tension control. So if once again, if you can remember that at this part, this is to be the strain here, let's say strain T, is to be equal to the strain as brought about by Fy. So Fy divided by strain Y, or strain U. Actually, this is to be 200,000. Modulus of elasticity. So 200,000. And at this particular point, so at this point here, the strain here should be 0.005. So ayun lang naman siya. And so with that, guys, if your strain is to be 0.005 and above, it means that your phi is to be 0.9 because we are in the tension controlled region. Tension controlled region. So if you can see here, guys, so if this is to be used in the equation before, so if this is to be used, your equation would now be equal to 0.85 betas of 1 fc prime times 3 over 8. And if you would be using NSCP provision, you would be using 3 over 7 instead of 3 over 8. Because in your NSCP, so NSCP allows the design up until this portion. So let's say that this is to be your strain T of 0.004. So it is to be at the transition zone. So transition zone. So there. And I myself, guys, if I am to design my concrete, it is better if I would be, in my case, in my opinion, it is better if you would be designing it as, using strain equal to 0.005 to assure that our section would be tension controlled and to ensure that my factor of safety, phi, is to be equal to 0.9. Because if you would be using this limit or this rho maximum, your value for your phi is not exactly equal to 0.9. So we have we will be solving for it via ratio and proportion. So that is to be the difference of both. Okay, so anyway, so nagka-commercial lang tayo because of this Romax. So once again, our main goal here is for us to get AS Max. And once that we have solved for AS Max already using your Romax, so once again, your AS Max is equal to your Romax times BWD. So once that you already know the value for your AS Max, you will now solve for it. So by the way, I will just be copying this to the next slide. So I will just be erasing this. Okay, so once again, once that you have already solved for AS Max, what you will be doing is that you will be getting the nominal moment of this section. So let's call it as MN1. So for MN1, you can solve for it using once again the strain diagram for your SRB. And let's say that for your MN1, if you would be getting the moment of about this point, so if you would be getting the moment about your tension side or your tension rebar, our MN1 is now to be equal to 0.85 times FC prime times A times B times D minus A over 2. So there, but we do not know the value of A yet. So it is up to you on how you would be solving for the value for your A. So you can either solve for the value for your A, either summation of forces horizontal. Then with that, guys, that is to be, so tension is equal to compression. So from that, AS max times Fy is equal to what is to be the compression, so 0.85 FC prime times A times B. So with this equation, guys, you can solve for A. So there are so many approaches as long as you arrive at the answer of A. So guys, reiteration that my method here is not to be the only way. So kung makaisip kayo ng bago, or if you notice something, or let's say that you will be deriving a shortcut very soon, then you can use that. So once again, this is just one of so many possibility of solving for our value of A. So this is to be the most typical one. So another way is for you to solve for Cmax. So Cmax, let's say. So Cmax, and for your Cmax, that is to be basically, so if you can remember from before, guys, so for the value for your C, this is to be 600 times D divided by 600 plus Fy. So am I correct? So I don't know if I'm correct, but assuming that this is correct, which I think it is, so this was actually derived from, so C, this is to be equal to strain U divided by strain U plus strain T times D. So it actually came from this equation. And if we would be substituting this, if we would be substituting all known values, so I will just be erasing this, by the way. Oops, sorry. So if you would be substituting all known values here, so once again, your strain U is to be equal to 0.003. So 0.003 divided by your strain U, once again, 0.003 plus strain T. And our strain T will depend upon which AS max you have chosen. So if you have chosen NSCP provision, which is this, so you would be substituting 0.004. And if you would be choosing this Romax here, you would be choosing 0.005. So assuming that we will be choosing this, it means that this is now to be 0.005 times D. So guys, take note that this is just one way. So shortcut lang to if you want to use it. Then if not, and if you want to use the more traditional way, which I did a while ago, or which I shown you a while ago, it will be up to you. But to save you some time in solving, you can actually use this. So simplifying this, guys, so this is now to be equal to 3 over 8 D. So ayan. So 3 over 8 D. So this is actually for tension controlled. So by NSCP provision, you can also use, so C is equal to 3 over 7 times D. So basically guys, if you would be looking at here, so this is to be the fraction that I have used. So if you can remember the derivation of this rho max from before, di alam nyo din na itong 3 over 7 na to nanggaling din yan sa value ng C max. Okay, so that is for C max actually, so C max. And after solving for your C max, so once, for example, that you have already solved for your C max, from there, you can now substitute your value for your C max at this equation. So your A is to be equal to, so betas of 1 C. So just multiply your C by betas of 1 and you can now solve for A. Then from that guys, you can now, you already have your value for your MN1. So all of these values right here are already known. So once that you already have the value for your MN1, so kapag meron na kayong MN1, you would now compare it with the value for your MU. So I would just be writing here once again. So compare MN1 with MN. I'm sorry, MN, not MU. So yung MN na na-solve natin is to be this. So compare it. If MN1 is to be greater than your MN, it means that you do not need to design this via DRB any longer. So with that, you will now be designing it via SRB. And for if MN1 is to be less than your MN, so this is to be the time that you will now be designing DRB or doubly reinforced beams. Okay, so going back here guys, so going back here at this equation, at this figure, so if this is to be the value for your MN, so looking at the green ink, so if this is to be the complete value for your MNs, so what that means is that this is to be the whole strength of your doubly reinforced beam. It is equal to MN1, which we have solved for a while ago, or this is to be the MN max for SRB. We would just be adding, so MN1 plus MN2. So your MN2, so just solve for this MN2. Or using the MN2, you can now solve for AS1 and AS prime. Okay, so with that guys, so we are already in step number 5. So step number 5, so change color. So step number 5. So if DRB, so assuming that your MN1 is to be less than your MN, I'm sorry, this is MN1. So if MN1 is to be less than your MN, you will now solve for MN2. So with that guys, so if you can remember, so the value for your MN is equal to MN1 plus MN2. So solving for the value of MN2, since you already know the value of your MN and MN1, so alam mo na tong dalawang to. So MN2 is now equal to MN minus MN1. So that is to be for the value for your MN2. And once that you already know the value of MN2, you can now solve for, where was that again? So you can now solve for AS1 and AS prime separately. So let's say that we will be getting the moment about this point. So let's get the moment about this point. So I think it is better if I would just be copying this to our text slide. For that slide, so step number 5. So if we would be getting the moment at this portion, so let's say at AS1 here, so let's say that we would be getting the moment there. And let's say that this is to be for the value for your D, or the effective depth, and this is to be for the value for your D prime, or that is to be the depth of compression rebar, so D prime, and this is to be D. So with that guys, our MN2 is now to be equal to, so once again guys, getting the summation of moment about this point. So AS prime, FS prime, times D minus D prime. So, ayan lang siya. And you have two unknowns here actually. So, you have an unknown here. So, AS is unknown, FS prime is unknown, D is unknown, and D is known and D prime is known. So, these two are unknown. So, what you will be doing is that you will be solving for FS prime using, of course, C balanced. C maximum. So, yung na-solve natin C maximum kanina, which is to be any of this. So, you can now solve for the for Fs prime here. So, guys, if you are wondering, hindi ba iba dapat sa C max? Iba dapat yung C dito sa area na to? So, di ba dapat iba yung C dito sa area na to? Hindi din dapat iba yung C dito sa area na to? So, basically, guys, they should be the same since they are to be in one system. So, magkasama naman kasi talaga sila. And kung iisipin nyo naman, kung if you are to be thinking that hindi ba mag-iiba yung C neto? Hindi ba mag-iiba yung value ng C neto if idagdag na natin to? So, short answer to that, guys. So, if you are to be curious that way, it is a very good question. But if you would be solving for it, since the value here or the value of your ASFY is equal to AS prime FS prime, they would just simply cancel out. Thus, the value for your C here would still be the same. So, kung hindi nyo naintindihan yun, it is better if you would be having an example problem later on. Okay, so, where were we? Okay, so going back here. So, from that, guys, so for your Fs prime, if you can remember your equation from last pre-recorded video lecture, this is now to be equal to 600 times C minus D prime divided by C. So, check if Fs prime is to be less than Fy, thus use Fs prime. So, use Fs prime. But let's say if your Fs prime is to be greater than or equal to your Fy, then use Fy. So, yun lang yun. You should already be familiar with that already. So, sorry. So, you should be already familiar with that since that is to be our topic for the past couple of months now. That if, let's say, your Fs prime or your Fs is to be greater than your Fy, you will now be using Fy. Okay, so that is for the value for your As prime. So, solve for As prime via shift solve or whatsoever, etc. And, well, basically, that is to be the answer already. So, that is for As prime. But what about for your As1? So, for your As1, get the moment about this point. So, paano ba kunin yung moment dyan? So, for Mn2 once again. So, Mn2 was already known a while ago. So, same lang sila neto. And this is now to be equal to AS1 Fy. So, guys, this is to be automatically Fy since we are deciding it as a tension controlled. So, tension controlled yan. Automatic Fy yan. Hindi na yan mag-Fs. Okay, so multiply this by D minus D prime. As you can see here, you only have one unknown. So, once again, we already have one unknown. And there, from this equation, you can already solve for AS1. Okay, so for the next step is for, of course, the detailing already. So, number 6. So, for the detailing, so we already have the value for your AS1, AS Max, and AS prime. So, both of these are for your tension reinforcement. And this is for your compression reinforcement. So, I would just be copying our figure once again here. So, ito na siya, collectively. Okay, so for a moment. Oops, sorry. So, if this is to be your section already, so your AS prime is to be this. So, this is to be your AS prime already. Then, as for your value for your AS, that is basically, so AS is equal to AS max plus AS1. So, this is for the value for your AS. So, now that you already have the value for your AS prime and AS, you can now determine the number of rebars by division. So just divide them by by the total area of one rebar for you to get the number of pieces. So from that, so paano ko ba isulat ng mas maayos? So for the number of compression bars, so number of bars, let's say prime, this is to be equal to AS prime divided by pi over 4 times the area of one rebar. So let's say dB squared. So same is true with our tensile reinforcement. So n bars, this is to be equal to AS. So take note that should be the total AS divided by pi over 4 times dB squared. Okay, so after solving for this, so n bars and n bars, you will now be checking the, so here, check spacing. So if you can remember, we have provisions from NSCP that SC, or the clear spacing, should be greater than or equal to 25 mm. SC should be greater than or equal to the diameter of bars, and SC should be greater than or equal to 4/3 of the maximum size aggregates. Okay, so for example, that it fills here, you can change your setup. So ayun lang naman siya. So let's say that this is to be your, what do you call this, your section, and you already have your compression bars here, and let's say that for your tension bars it was inadequate in spacing, you can rearrange it in such a way that, let's say you will be having 2 layers. So let's say 1, 2, 3, 4, 5. So you can do it this way. However, you must resolve for it since the value for your D will now change. Kasi kung kanina, kung ito yung value ng D mo, that wouldn't be the case any longer because you would be having 2 layers and the effective depth should be measured from the centroid of your steel rebars. So there, so it should be in this particular manner. Okay, so we would be having an example problem in the next video. So I think it is already 30 minutes. So next video na lang yung mismong sample problem natin for the design of our doubly reinforced beams.